Let us discuss on some applications of potentiometric analysis. So as you know, potentiometry is a suitable quantitative technique for determining the amount of the analyte present in the sample. So it may be by measuring the EMF or by measuring the pH, whatever it is. The pH or the EMF will be related to the concentration of the analyte. Therefore, potentiometry is an important tool to determine the concentration of the analyte in quantitative applications. And even in clinical chemistry or environmental chemistry laboratories, the concentration of the active species, it is called as analyte, can be determined by using the relationship between the concentration and the EMF as related in Nernst equation. And more importantly, most of the potentiometric titrations are performed because in order to quantify the species. So in order to quantify the species, the chemist or the analyst must aware of what is the relationship existing between the cell potential and the analyte concentration. So this is given in the Nernst equation. What is the relationship between the cell potential and the analyte concentration? One must aware. If you know the relationship between the concentration and the cell potential, then only it will be very easy to determine the concentration of the analyte. Okay. And after knowing the relationship between the concentration of the analyte and the cell potential, before using the potentiometric technique, we must have the knowledge of standardization of the procedures. It may be standardizing the potentiometer, it may be standardizing the electrode, or it may be standardizing the standards of what you are using in the potentiometric method of analysis. So while using the potentiometric technique, you must have the knowledge about some limitations in the Nernst equation. So what we will write in the Nernst equation? E cell is directly related to the concentration of the metal or concentration of the analyte. It may be in the molecular form or in the ionic form. Consider a metallic indicator electrode or a membrane indicator electrode. We will write the Nernst equation. That Nernst equation is relating the measured cell potential and the concentration of the analyte. If it is a metal, E cell will be E naught minus 0.0591 divided by N into log of 1 over concentration of Mn plus, where E naught can be replaced with a new constant K if it is membrane potential. So we are ignored while writing the Nernst equation that not the concentration of the analyte but the activity of the analyte must be written. So if you replace the concentration of the analyte by the activity, the Nernst equation will be converted to E cell is equal to K minus 0.05916 divided by N into log of 1 over activity of the metal, activity of the ion, activity of the analyte, where the activity of the analyte, as you know, is related with the concentration of the analyte or the metal or the ion and the activity coefficient denoted by gamma n plus. If you substitute this in place of activity, you will be getting the new Nernst equation, that is E cell is equal to K minus 0.05916 divided by N into log of 1 over gamma n plus minus 0.05916 divided by N into log of 1 over concentration of Mn plus. Here this Mn plus is analyte, this gamma n plus is the activity coefficient. So while using this particular equation, how to obtain the concentration of the analyte, how to simplify to that? If the activity coefficient is known, if this value is known, then there will be no problem. If this value is known, this whole term will be constant, and the standards and the sample are having identical matrix, then only this value will be constant. If the matrices present in the sample and the standards are known and identical, then only gamma n plus will be constant, and hence this term will be constant. If this term will be constant, this constant and this constant will be giving you a new constant that can be denoted as K dash minus 0.05916 divided by N into log of 1 over concentration of analyte. So the concentration of analyte is directly related to the EMF of the cell. So this is the way in order to relate the activity of the analyte and the EMF of the cell. Activity is replaced by the metal ion concentration if the activity coefficient is known and constant. So this is how we have to consider the activity in place of concentration in the relationship between the concentration of the analyte and the EMF of the cell. And in quantitative applications, we will be using the external standards, and the purpose of using the external standards is to construct the calibration curve. So, in order to determine the concentration of the analyte, we need a calibration curve. Before obtaining the calibration curve, we have to standardize the analytical procedure, including the electrode. Suppose, say for example, if you immerse the glass electrode to a solution of 0.05 molar PHP, potassium hydrogen phthalate, the glass electrode should show the pH of 4.02. It should not show 4.2 or it should not show 3.9. So you have to calibrate, you have to standardize the electrode. After the standardization, if the response from the electrode obeys the Nernst equation, then the standardization with a single external standard is possible. If the Nernst equation is not obeyed, the standardization with the external standard will be impossible. So how do you come to know the standardization is proper? You will construct a calibration line of E cell versus concentration of the analyte or logarithmic concentration of the analyte. That calibration line will be giving you the slope value of plus or minus RT by NF or plus or minus RT by ZF, where N is the number of electrons or Z is the charge on the analyte. Then if the calculated slope, experimentally obtained slope is almost the same or almost identical to plus or minus RT by NF or plus or minus RT by ZF, then you can say the calibration line is ideal, otherwise it will be non-ideal. Such analytical procedure will be denoted as a suitable procedure with ideal Nernstian behavior, and the slope obtained, if it is matches with 0.05916 volts or 59.16 millivolts, then you can say it is Nernstian slope, otherwise no. So the electrode is also able to respond to analyte's activity. Therefore, if you take series of solutions of increase the concentration of the analytes, of course in the absence of the interference, the calibration curve between E cell and the activity will be a straight line. However, if the interferences are there, if the interferences are there, then the calibration curve of E cell versus activity will be curved. There will be a curvature. But the calibration curve without the curvature or with the curvature, both are useful in determining the Nernstian slope and hence the concentration of the analyte. So the curvature is due to the matrices present. The curvature is due to the matrices present. So in order to eliminate the curvature, in order to reduce the curvature, what you can do, the best way is you have to match the matrix. Means you have to add the matrices into the standards, and those matrices must be same as those present in the sample. So that is called as matrix matching. But if the sample composition is unknown, what are the matrices present in the sample is unknown, then matrix matching will become impossible. So the construction of the calibration curve is very important, as you do in spectrophotometry. What do you do in spectrophotometry? You will prepare a standard solution of known concentration. You will measure the absorbance for that. Then you will plot a graph of absorbance versus concentration. That will be a line, straight line. That is called as calibration line. So likewise, here also, the calibration line between E cell and negative logarithm of concentration of analyte will be a straight line, or E cell as a function of logarithmic concentration of analyte is also a straight line. But here only logarithmic concentration of analyte, here negative logarithmic concentration of analyte. These are mirror images to each other. If you put minus logarithmic concentration of analyte in the abscissa, this curve will be mirror image to the straight line obtained while considering only logarithmic concentration of the analyte. So these are ideal curves where the Nernstian slope will be obtained. Therefore, these are ideal curves, ideal calibration curves. Some non-ideal behaviors are also seen. Therefore, there will be a curvature. The calibration lines are curved like this. In such cases, only linear portion will be considered in order to calculate the slope, and hence in order to calculate the concentration of the analyte. Here it may be lead, or here it may be immunoglobulin, whatever it is. So linear portion you consider, you calculate the slope, then use that slope to calculate the concentration of the analyte. So this is how we will be using the standards, external standards in order to construct the calibration curve. You construct the calibration curve, take the sample, measure the EMF, locate the EMF value in the ordinate, then you interpolate to the abscissa into the x-axis, find out the value of logarithmic concentration of analyte or minus logarithmic concentration of analyte, then you can find out the concentration of analyte very easily. Apart from the usage of the external standards in order to construct the calibration curve, if the matrices are known, we can also follow the addition of the standard inert electrolytes in large excess in order to balance the activity coefficient, in order to make the activity coefficient as a constant value. So what do? You will be taking the sample as well as the standards. Then you will add an inert electrolyte such as potassium nitrate or sodium nitrate in excess, almost 10 or 20 times more than the concentration of the analyte present in the sample or in the standard. You will add it. What will happen if you add that? The ionic strength of each solution will be adjusted. Therefore, the activity coefficient in each solution will be constant. So there is no appreciable role played by the matrices. This electrolyte, the inert electrolyte what you are going to add is called as total ionic strength adjustment buffer, because its role is to adjust the ionic strength. Therefore, its name total ionic strength adjustment buffer. So this will be done by adding an inert electrolyte at high concentration to the standards as well as the sample. As a result of the addition of this total ionic strength adjustment buffer, the activity coefficient remains essentially constant. Therefore, we can eliminate the curvature in order to get ideal calibration line. Apart from this, we will also be using the standard addition technique. In potentiometry, we will also be using standard addition technique. Whenever the concentration of the analyte present in the sample is low, too low, we can spike a standard to the sample. Therefore, we can enhance the concentration of the analyte in the sample. Therefore, without any error, we can determine its concentration. Why do we do this standard addition? Standard addition will be done in order to eliminate the difficulty while maintaining a constant matrix in samples as well as standards. We will not be knowing what are the matrices present in the sample and the standards. So, in order to eliminate this problem, we will follow standard addition procedure by using a standard of known concentration. So, the difficulty of maintaining a constant matrix for samples and standards will be eliminated. How do we do this? Let me take an example. In the analysis of a sample containing analyte X, we will be following standard addition procedure. How do we do this? You take a sample of volume Vx containing the analyte of concentration Cx, you transfer this into a potentiometric cell and measure the EMF, that is going to be E cell of X. So, because analyte is present, therefore E cell of X is developed. The developed E cell of X is related to concentration of analyte. That can be written by using Nernst equation. E cell of X is equal to K plus 0.05916 divided by N into log of concentration of analyte, that is Cx. Let me call this equation number 1. Afterwards, what do? You take the sample, you take the standard. First you measure the EMF for the sample of volume Vx containing analyte concentration Cx. You have measured the E cell, that is E cell of X. that is related to concentration of analyte Cx. Then you take the standard. You measure the volume Vs of standard containing a fixed quantity of the analyte Cs. Cs is the concentration of analyte present in this Vs. You spike into this solution. What you have taken Vx of the sample. You spike the standard of volume Vs into Vx. Then you measure the EMF, that is going to be E cell S. After the standard addition done, you measure the EMF. Then the EMF is related to the concentration of the standard and the concentration of the analyte, because it is containing both Cx and Cs. So E cell of S is equal to K plus 0.05916 divided by N into log of Vx into Cx divided by Vt plus Vs into Cs divided by Vt, where this term will be giving you the total concentration of the analyte in the sample and in the standard. What is the total concentration of the analyte in the sample is Vx into Cx divided by Vt, and what is the total concentration of the analyte in the standard is Vs into Cs divided by Vt. So Vt is the total volume, that is summation of Vs and Vx after standard addition. Vs volume you have taken for standard and Vx volume you have taken for sample. Summation of both you will be getting Vt. Assume if Vs volume of the standard is significantly lesser than volume of the sample. You have to make one assumption, that is the change in the sample matrix can be ignored and the activity coefficient will be constant. If the value of Vs is significantly lesser than Vx, the activity coefficient will be remaining constant. Then what is the relationship between concentration and activity? Activity is same as concentration. So Vs is such a smallest volume, what you are going to spike. You subtract equation 1, that is this equation, this particular equation, that is giving the relationship between the concentration of analyte in the sample and the potential measured for the sample, and the total concentration of analyte after the standard addition procedure and the total potential. Equation 2 minus 1 gives this particular equation. E cell of S minus E cell of X is equal to K plus 0.05916 divided by N into log of Vx into Cx divided by Vt plus Vs into Cs divided by Vt minus K plus 0.05916 divided by N into log of concentration of analyte, that is Cx. Let me take the common factor 0.05916 divided by N as a common factor. So this term will be giving you 0.05916 divided by N whole into K plus log of Vx into Cx divided by Vt plus Vs into Cs divided by Vt minus K plus log of Cx. So N will be shifted to left hand side, and difference between E cell of S and E cell of X will be giving you delta E, the change in EMF. Let us write it simply. So N will be shifted to left hand side. So N into delta E, 0.05916 I will shift to denominator because it is present in RHS as a common factor. When it is shifted to left hand side, that will come to the denominator. So N into delta E divided by 0.05916 is equal to log of Vx into Cx divided by Vt plus Vs into Cs divided by Vt minus log of Cx, where plus K and minus K will be getting cancelled. Plus K and minus K will be getting cancelled. So this is left with only log Cx minus log Cx. So finally, you will be getting N into delta E divided by 0.05916 is equal to log into Vx divided by Vt plus Vs into Cs divided by Vt divided by Cx into Vt, because this is in the form of log M minus log N. Log M minus log N will be simply written as log M by N. So log of Vx into Cx divided by Vt plus Vs into Cs divided by Vt divided by Cx it will be. Cx divided by Cx will be cancelled. Therefore, this term will be left with Vx by Vt. Here Vs into Cs divided by Cx into Vt. This is the final equation. We will be knowing the value of N. This may be either charge or number of electrons. Delta E, the change in EMF before the addition of the standard, and after the addition of the standard, you can take the difference in EMF. Vx is the volume of the sample, Vt is the total volume, Vs is the volume of the standard, Cs is the concentration of the analyte in the standard, and hence you can calculate the concentration of analyte in the sample. This is a simple example in order to illustrate the standard addition procedure in potentiometry. This is simply the determination of calcium ion concentration in seawater. 10 ml seawater was taken and diluted to 100 ml, and out of which 50 ml was drawn and placed in a potentiometric cell, immersed calcium ion selective electrode and reference electrode, measured the cell potential, that is minus 0.05290 volts. Then, after the measurement is over, 1 ml of the standard containing calcium was added. Its concentration is 0.05 molar. 0.05 molar. After the addition of the standard calcium to the sample, again EMF was measured, that is minus 0.04417 volts. What is the concentration of calcium in the seawater? So this is Ex because EMF measured to the sample. This is Vs, volume of the standard. This is Vx, volume of the sample. This is Cs, concentration of calcium in the standard. This is the EMF after the standard addition is made. So delta E you can calculate. Delta E cell of the standard calcium is minus 0.04417 minus of minus 0.05290 is equal to 0.00873 volts. This is going to be delta E. Volume of sample is given Vx and Ex is given, delta E is given, Cx you have to calculate, Vt is 50 plus 1 ml, 51 ml. So you substitute this into equation 3, you can simply calculate the concentration of analyte. So N is 2 for calcium, because calcium is divalent. N is 2 into delta E is 0.00873 divided by 0.05916, it is retained, is equal to log of Vx is 50 ml, 50 ml of seawater after dilution was taken. Vt is 50 plus 1, that is 51 ml, plus volume of the standard is 1 ml, concentration of calcium in the standard is 0.05 molar or 5 into 10 power minus 2 molar, divided by concentration of the analyte, concentration of the calcium in the seawater unknown, we have to determine. Vt is 51. So if you further simplify, you will be getting 0.2951 is equal to log of 0.9804 plus 9.804 into 10 power minus 4 divided by Cx. So after all rearrangement can be done very simply. You take inverse log on both sides. So we'll be ending up with Cx is equal to 9.88 into 10 power minus 4 molar. Cx is equal to 9.88 into 10 power minus 4 molar. What does this mean? This is the concentration of calcium present in 50 ml of the seawater. Which 50 ml? 10 ml original seawater was diluted to 100 ml. In that 100 ml, 50 ml was used, and it is containing 9.88 into 10 power minus 4 molar calcium. What is the dilution factor? 10 ml of seawater was diluted to 100 ml. So dilution factor is 10. 10 times 10 tens are 100. So 10 times the seawater was diluted. So you have to multiply this by 10 times. So you will be ending up with 9.88 into 10 power minus 3 molar. This is the concentration of calcium present in seawater. What is that seawater? 10 ml sample, what you have taken, what was withdrawn from the sea. So the concentration of calcium present in seawater is 9.88 into 10 power minus 3 molar. So this is called as standard addition procedure. To the seawater, standard solution of calcium of known concentration was added, then concentration of calcium in seawater was determined. So therefore this is called as standard addition procedure. Apart from standard addition procedure, it is very important to understand the selectivity of the potentiometric technique while determining the concentration of free ions against complex ions. Let me assume that the determination of fluoride by using fluoride ion selective electrode. So you know working principle of fluoride ion selective electrode, it is selective for the determination of only fluoride ion, not the hydrogen fluoride or the free fluorine. It is applicable for determination of only fluoride. So after immersing the fluoride ion selective electrode and the reference electrode, the solution should have a pH of greater than 4. Then only this equilibrium reaction will be expected. HF plus H2O gives rise to H3O plus F minus if pH is greater than 4. If the pH is less than 4, fluoride will be in equilibrium, fluoride will be present in the predominant form of HF. Fluoride ion selective electrode will not be useful to determine HF. It is useful to determine only fluoride ion, not hydrogen fluoride. Hydrogen fluoride is a molecule, fluoride is a ion. So ionic fluoride can be determined by fluoride ion selective electrode, not the hydrogen fluoride. So potentiometric procedures are dependent on the experimental parameters too. So here important parameter is pH. If you maintain the pH greater than 4, then only the equilibrium of this particular reaction will be shifted from left to right. So HF is going to be ionized to obtain F minus. Then selectively fluoride ion selective electrode will be functioning for determination of fluoride. Another example, let me give you why potentiometric technique is suitable only for the determination of concentration of free ions. Let me aim to determine calcium amount in urine. Urine will be containing two types of calcium. One is ionic calcium and other one is calcium bounded to protein. Ionic calcium will be freely available in urine, so that can be easily determined by potentiometry with calcium ion selective electrode. But protein bound calcium cannot be. If you compare the selectivity of atomic absorption spectrometry is suitable to determine total calcium because you will be subjecting the sample for sample preparation where protein bounded calcium will be converted into free calcium. So calcium will be aspirated onto the flame. After aspiration, even proteins undergo combustion to convert carbon to carbon dioxide, nitrogen to nitrogen dioxide, etc. So therefore only free calcium will be aspirated. So calcium will be aspirated onto the flame in order to get the orange flame. So the intensity of the orange flame will be measured in flame photometry or in absorption spectrometry. Or what are the total number of atoms left over in the ground state will be measured. Therefore, total calcium can be determined by AAS. But by potentiometry, by using calcium ion selective electrode, only free calcium can be measured. So therefore, potentiometry is limited only for the determination of analytes in their free states, not in the complex states. So if the analyte present in the complex form, potentiometry is not selective. It is selective only for the determination of analytes whenever they are present in free states. Let us move on to the usage of potentiometric technique in order to measure the pH. So pH is nothing but the hydrogen ion concentration. When you record the pH by using glass electrode will not only respond to hydrogen ion but also to the matrix. So whatever the pH you are recording is completely relied on the composition of the matrix. So there is uncertainty in measuring the pH, particularly the uncertainty in the relationship between the potential and the activity, as I told in the previous slide. There are uncertainties while relating potential and the activity. Let us see that. By using the combined electrode or pH electrode or glass electrode, we can give the definition for pH that negative logarithm of hydrogen ion concentration. Also, pH can also be written as negative logarithm of activity of hydrogen ion. Okay, according to this equation, you use 0.1 molar hydrochloric acid to measure the pH. pH will be 1. If you measure the pH of 0.1 molar HCl, according to this particular equation, pH will be 1. So, this is the experimental. but the actual pH will be 1.1. 1.1 is greater than 1. Why this 0.1? 10% error. 1.1 to 1 is having 10% error. So this 1.1 is obtained according to this particular equation. So why this difference? This difference is due to the activity coefficient. That is, the activity coefficient for hydrochloric acid, the activity coefficient for hydrogen ion in hydrochloric acid is not unity, because HCl has a matrix of chloride. HCl has a matrix of chloride. Therefore, we can come to the conclusion that pH is dependent on the composition of the solution for which we are going to measure the pH. Similarly, you consider 0.01 molar HCl in water. The aqueous solution of 0.01 molar HCl will be having a pH of 2. But if you add a matrix of lithium chloride of concentration 5 molar, lithium chloride is a neutral species, neither acidic nor basic, just like sodium chloride. So it should not decrease the pH. But if you measure the pH of hydrochloric acid of concentration 0.01 molar in 5 molar lithium chloride, pH will be shifted to 2 acidic level, 2 to 0.8. Why this is? This is due to the matrix lithium chloride. So the composition is also matters. Composition is also matters. So what is the conclusion you can give for this? Because of all these reasons, you have to calibrate the electrode properly. What is the solvent you are going to use to prepare the standards? The same standard must be calibrated. The same solvent must be used to calibrate the instrument. It's very important to understand. Okay. Say for example, how to eliminate these uncertainties while measuring the potential which is having a relationship with the activity. Let me take an example. For a glass membrane electrode, we will be measuring the EMF, that is Ex, for any unknown, which is having an unknown pH, and the Nernst equation can be written in this fashion. Ex is equal to this Ex, the E cell, what we will measure by means of glass electrode for any solution of having unknown pH, is equal to K minus RT by F into ln 1 over activity of H plus, which can further simplifies to K minus 2.303 into RT by F into pH of X, where pH of X means unknown pH. Let it be equation 1, where all the contributions to the constant K are subject to uncertainty and they subject to change from day to day, as well as electrode to electrode. The value of K will be deviated from day to day as well as electrode to electrode. Okay, so you will be doing the calibration using a buffer of known pH. Suppose you will be using acidic buffer or you will be using a basic buffer of known pH. For the buffer solution, there is a relationship between ES and the pH is existing. So that ES can be written as K minus 2.303 into RT by F into pH of the standard. This pH of the standard means it is a known pH of the standard buffer. So let this equation be 2. Subtract equation 2 from 1, we will be getting ES minus EX. ES minus EX will be equal to K minus 2.303 into RT by F into pH of S minus K plus 2.303 into RT by F into pH of X. So you need to obtain the pH of the unknown. You simplify. pH of the unknown is equal to pH of the standard minus EMF of the unknown minus EMF of the standard whole into F divided by 2.303 into RT. Let me call this equation number 3, where F is the Faraday's constant, R is the universal gas constant, T is the temperature. If you put in place of F 96,487 coulombs, in place of R 8.314 joules per Kelvin, T 25 degrees Celsius, and if you convert that into Kelvin, you will be getting 298 Kelvin. 96,487 here, 298 in place of T, 8.314 in place of R, will be getting 0.05916 into EX minus ES. So pH of X is equal to pH of standard minus EX minus ES divided by 0.05916. So why do we do this? Why this equation is required? While calibrating the pH meter or while calibrating the potentiometer in order to measure the pH, you need to have the pH of the standard, EMF of the unknown and EMF of the standard. Then only you can have the correct value of the pH, accurate value of the pH for the unknown. So this is an important relationship, and this is not only applicable for the glass electrode or pH electrode or hydrogen ion selective electrode. Glass electrode or pH electrode is also called as hydrogen ion selective electrode. Any ion selective electrode you construct, the PM, if M is any ion, PM of X is equal to PM of S minus EX minus ES divided by 0.05916. Any ion selective electrode if you are constructing, or any ion selective electrode you are using for measurement of analyte concentration, this equation will be holds good to calculate the accurate concentration of the analyte by means of PM value. So let us demonstrate that later. So how do you calculate the pH meter? This is very important because you are using the pH meter right from your PU level. How to calibrate the pH meter or the pH electrode? Usually the calibration will be done by using the standard buffers, particularly pH 4.01 or 7 or 9.18 buffers. What do? You take the standard buffer. Say instead of buffer, even you can use 0.05 molar PHP. That can be used as 4.015 standard, 0.01 molar borax as a 9.18 pH standard, or 0.025 molar potassium dihydrogen orthophosphate as 6.865 standard in place of 7. So if you have PHP solution, potassium hydrogen thalate solution of concentration 0.05 molar, that can be used as a standard buffer to calibrate the pH meter to pH 4.015. Similarly, borax for pH 9.2 or 9.18, or potassium dihydrogen orthophosphate for pH 6.865. To take the pH meter, immerse the electrode, connect the electrode to the pH meter, immerse the electrode into either acidic or basic buffer, that is dependent upon the scenario or the situation. If you are wanted to measure the pH of the unknown, and if the unknown solution is acidic, you have to calibrate the pH meter with the acidic buffer. If the pH of the unknown is basic, you have to calibrate the pH meter with the basic buffer. So you immerse the pH electrode into the buffer, standard buffer, adjust the pH knob so that the accurate pH must be displayed by the pH meter in such a way that 4.015 or 9.18 or 6.865. Then you remove the electrode, then you take the neutral buffer, adjust the temperature knob so that the pH should be showed at 7. Don't disturb the pH regulator because it was already adjusted. Once the pH is adjusted to standard value, immerse the glass electrode in a neutral buffer. You rotate the temperature knob in such a way that temperature must be adjusted to obtain the pH of 7. So that pH 7 will be displayed by the pH meter. This is how we will be calibrating the pH meter. You do remember? Take the electrode, immerse into any standard buffer, rotate the pH knob to obtain the required value. Then you remove the electrode, immerse into the neutral buffer. Then adjust the temperature to get the pH of 7. This is a simple example how the calibration is going to be important in order to measure the pH of any unknown solution. Okay, this is a representative example. A glass electrode was used and measured the EMF of 0.395 volts against saturated calomel electrode at the standard pH of 7. What is the pH of the unknown? Which has showed the potentials of 0.467, 0.209, 0.08 and minus 0.013 volts. So this equation is going to be very useful now. pH of the unknown can be calculated by using this particular expression, which is having pH of the standard minus EMF for the unknown and EMF of the standard divided by 0.05916. So given pH of the standard is 7 because standard buffer having pH of 7. EMF of the unknown is given here 0.467 or 0.209 or 0.08 or minus 0.013. EMF of the standard is, it is a buffer having standard pH, that is 0.395. What is pH of the unknown? Now the equation, pH of the standard is 7 minus EX is 0.467 because this has 4 sub-problems. 0.467 minus ES is 0.395 divided by 0.05916. You're going to get 5.78. So the pH of the unknown is 5.78. So this is how you can do the calibration and you can encast that in order to obtain the pH of the unknown solution. Similarly, the other potentials you can substitute and you can have the pH of other unknown solutions. Similarly, the pH of the acetic acid solution can also be recorded. Glass electrode and saturated calomel electrode pair is calibrated at 25 degrees Celsius by using 4.01 standard buffer. The EMF for the standard is 0.814 volts. If you take 1 millimolar acetic acid solution, what is the voltage generated? Given that activity of H plus ion in acetic acid will be simply hydrogen ion concentration. pH of the standard is given 4.01. You have to calculate the EMF for the acetic acid. EMF for the standard is also given 0.814 volts. Right? pH of the X is not known. Because concentration of acetic acid is given, you have to calculate the pH. For acetic acid, pH is not equal to negative logarithm of hydrogen ion concentration. So we have to use the dissociation equilibrium. Acetic acid in water in aqueous solution will be dissociated to give acetate ion and CH3COO minus and H3O plus. So the dissociation constant will be equilibrium constant. By using that expression, Ka is equal to concentration of acetate into concentration of H3O plus divided by acetic acid concentration. So H3O plus concentration is equal to acetic acid concentration divided by dissociation constant divided by acetate ion concentration. If you use principles of law of mass action and you calculate H3O plus concentration, by means of that you can calculate the pH. You can calculate the pH. So the pH of the 1 into 10 power minus 3 molar acetic acid will be 3.88. You must remember the first semester theory about the dissociation of acetic acid, titration of weak acids versus strong bases. So use the law of mass action and dissociation equilibria, you will be getting the pH of 1 into 10 power minus 3 molar acetic acid as 3.88. Then pH of the standard is 4.01 minus EMF of the acetic acid is unknown. You keep it as such. EMF of the standard is 0.814 divided by 0.05916. So you will be getting EMF of the unknown as 0.822 volts. So this is how, by means of calibration, you can determine the pH of any unknown. As I told you, the calibration is useful for any ion selective electrode. You have to do the calibration for any ion selective electrode. This is such example. Sodium ion selective electrode is used to measure the sodium ion concentration. So the electrode was immersed into sodium ion solution. Sodium ion selective electrode was developed, fabricated and used to determine the concentration of sodium ion in the unknown, which was immersed and developed a potential difference of minus 0.2331 volts. And the volume of the unknown is 10 ml. Standard addition was made. 1 ml of 0.02 molar sodium chloride was added. And the total EMF in the presence of sodium in the sample as well as sodium in the standard will be looking the development of minus 0.1864 volts potential. What is the concentration of sodium in the original solution? Means in this unknown solution, what is the concentration? So PNAS is equal to 1.699. PNAS means sodium in the standard. This is the standard. Concentration of sodium in the standard is 0.02. So negative logarithm of 0.02 means PNAS, that is 1.699. EMF of the unknown is minus 0.2331 volts. Here it is given minus 0.2331 volts. ES is equal to total EMF, that is minus 0.1864 minus EMF for the unknown. Total minus EMF for the unknown, you will be getting EMF for the standard. EMF for the unknown is minus 0.2331 volts. So that is 0.0485 volts. So PNAX, what you have to calculate? PNAX is equal to PNAS minus E unknown minus ES divided by 0.05916. PNAX will be 6.46. So if you take PNAX is nothing but minus log of Na plus concentration minus log of Na plus concentration. You take anti-log of minus 6.46, you will be getting concentration of Na plus as 3.46 into 10 power minus 7 molar. So this is how, by doing appropriate calibration, you can determine the unknown concentration of the ions or the analytes present in any sample solution. So apart from such applications for the measurement of pH or the metal ion concentration in any sample, potentiometry can be widely used for the determination of clinical samples. That too for the determination of electrolytes such as sodium ion, potassium ion, calcium ion, hydrogen ion, chloride ion, and carbon dioxide, and some other dissolved gases. All these ion selective electrodes you are aware. Chloride ion selective electrode you can construct by using silver sulfide, silver chloride crystal. Sodium ion selective electrode by modifying Corning 015. Similarly, potassium ion selective electrode, calcium ion selective electrode, liquid based membrane electrode, hydrogen ion selective electrode, that is pH electrode, gas sensing probes, carbon dioxide sensor can be used in order to determine the concentration of the respective analytes in any clinical samples. Of course, for extracellular fluids such as blood and urine, the analysis have to be made in vitro with the conventional electrodes. Direct analysis is not possible, but in vitro analysis can be made by conventional electrodes. Means for individual species, individual electrodes must be designed. Suppose for glucose, glucose sensor. For uric acid sensor. For urea sensor can be used. Of course, the interferences must be eliminated. And some automatic analyzers are available in the clinical laboratories. They have the ability to analyze several hundreds of samples simultaneously. So they will be having individual flow cells. Individual flow cell will be having individual analyte selective electrodes, and they will be allowing several analytes to be monitored. So within 10 minutes, at least 100 to 1000 species can be quantified by using automatic clinical analysis. So therefore, clinical applications are very wide for potentiometric techniques. And potentiometric technique is not as much as applicable for environmental samples analysis, but it is suitable. Potentiometric technique is highly selective technique, provided a suitable ion selective electrode is available. Say for example, cyanide, fluoride, ammonia and nitrate in water sample can be determined very accurately by using suitable electrodes. And even platinum electrode is very useful to determine the concentration of nitrate, provided nitrate can be converted into amine. Nitrate can be converted into amine by suitable reduction process. Ammonia can be detected by pH electrode, fluoride by fluoride ion selective electrode, cyanide by cyanide ion selective electrode constructed by using silver sulfide and silver cyanide crystal. So therefore, the environmental samples such as wastewaters can be subjected for analysis by potentiometry. So, say for example, for fluoride, as I told you, because of the equilibrium principle, the other analytical techniques such as AAS, some other techniques, fluoride is selectively determined whenever fluoride is present in free state. If the pH of the solution is greater than 4, then only fluoride and selective electrode will be suitable. Otherwise, we can go for spectrometric technique. In spectrometry, less than 5 ppm fluoride can be determined. In such cases, potentiometry will be less selective. So, as I told you already, by incorporating the suitable ion selective electrode into the flow cell, continuous monitoring of the ions or the analytes can be made in automatic samplers and automatic analyzers. Therefore, in such cases, potentiometry will be having widespread applications. And even the research is still on for the development of biosensors. You can take glucose biosensors, you can take even pharma biosensors, you can take uric acid biosensors, you can take enzyme biosensors. The research is vast. If you look onto the articles published in the fields of biosensors, a huge amount of work has been devoted because of the principle of potentiometric technique. Whatever it is, either chemosensor or biosensor or ion selective electrode or solid state crystalline membrane electrodes or liquid based ion selective electrodes, whatever it is, the principle behind the functioning of each and every sensor remains the same. There must be relationship existing between the concentration of the analyte and the EMF of the cell, and the electrode calibration must be known to the worker. Then only there will be a fruitful outcome. Therefore, the research is still on in developing the biosensors. So these are the applications of potentiometric techniques. So thank you for your patience.